thank you. It's good to be back. So I guess my main motivation for speaking here today is that I realized in my own life in college and most of my friends at the University of Pennsylvania and other universities, research is really a central feature of academic experiences. I know that research has this kind of scary connotation while you're in high school and everything, but really it's foundational to university life. And if you want to go into most careers and really any kind of graduate school nowadays, given especially the competitive nature of applications now, you really need to do research in your field in college. So my research is centered in medicine, as I want to be a doctor, but research is really available across the disciplines in humanities, in history, art, fine arts, literature, also in physics, chemistry, and so on. So I'm just going to take you through one of my projects from start to finish. This is one that I've designed and I've been with for the past 3 years. And it's one that's very dear to me because I really think the result is truly remarkable and has sweeping effects in the field that I'll talk about. So here we go. I work in the craniofacial research laboratory, which is part of the Division of Plastic Surgery at the Children's Hospital of Philadelphia. And I'm going to talk to you about growing bone that we use to help reconstruct faces. I have no financial disclosures regarding this project, and it was all funded by grants from the Department of Defense and the National Institute of Health. So just to focus on our lab, the craniofacial lab at CHOP focuses on children that have disfigurements of their face, and basically from the middle of their chest up due from birth. And really we work to try and correct these. And while we are a research laboratory at the bench, we work very closely with the team of plastic surgeons that perform these operations every day, and our lab is what we call translational. We try and take the concepts that we work with at the bench and immediately bring them forward into the clinic. This is as opposed to basic science, which is kind of just like test tube work. We are always thinking of how this can affect the patient immediately. So as you can see, we take our ideas from the clinic to the laboratory to the clinic immediately. So let's begin by throwing away some societal misconceptions about plastic surgery. Plastic surgery is concerned with the duality of form and function. Form is what something looks like, and function is what something does. You guys probably think of plastic surgery as facelifts and nose jobs and breast implants and liposuction. Really, this all falls under the umbrella term of cosmetic plastic surgery, which makes up only about 30% of procedures nationwide every year. Other plastic surgery, the other 70%, is called reconstructive. Reconstructive means that we restore form and function to some part of the body that was damaged in some way, be it through a car accident or a war wound or a birth defect. At the bottom here, you see two examples. This is a baby with what's called a cleft lip. A cleft lip is basically where the lip is cut in two. And you can see that this really affects both the baby's form and the function. Obviously, it looks weird. It's not normal. And secondly, it affects the baby's ability to eat, eventually to speak, to breathe, and so on. So the corrective surgery for that would fall under reconstructive surgery. On the right, you see a typical rhinoplasty. This is a nose job. This generally is a more cosmetic procedure. You can see that there's a bump in the nose, and they shave it down to give a straight nose. Really, while this is generally cosmetic, it also restores form and function because a lot of people who get rhinoplasties get them for secondary reasons of problems breathing, problems speaking, and so on. Plastic surgery originally emerged way back in the first millennium BC, actually with an Indian physician named Sushruta, who performed kind of controversial and weird experimental surgeries on women in his community. But more modern, around the First World War, we were introduced to weapons of mass destruction of a certain scale, and soldiers came back from war with these horrible injuries that weren't really seen to this point. So the first plastic surgery department was actually established at where I go to school, the University of Pennsylvania, and their goal was to kind of restore a sense of normalcy to these soldiers who were coming back. What you see is a picture of Walter Yeo. He's a U.S. naval officer from 1917. This is the first recorded plastic surgery operation in the world. You can't really see so often in the picture because it's a bad quality picture, but he had from his nose up was completely burned off by a chemical explosion. And while it looks somewhat normal, he's actually missing his eyelids and most of the skin above his nose, and he's very close to death actually at this picture. So what doctors did was they performed a skin graft where they took skin from his thigh and they brought it back up and they restored a lot of function to his face. So this is actually truly an amazing result. It just doesn't look so much for our day, but for that day, almost 100 years ago, it was unbelievable. So let's center in on reconstructive surgeries. Here you see 3 very common cases of procedures that require reconstructive surgery. On the far left, you see a girl she had a tumor that took up about 1/4 of her skull. She's actually at the Children's Hospital of Philadelphia. And the only way the doctors were able to save her life were to remove literally 1/4 of her skull. The only thing separating her brain from the outside air is a flap of skin. In the middle, we see a 3-month-old baby, also at CHOP, with what's called craniosynostosis. Basically, if any of you have ever held a baby or played with a baby, the baby has soft spots on its skull. This is because the skull is slowly forming over the course of your young adult life. So this baby basically has a disorder where the skull forms too quickly, and therefore the body doesn't have time to grow the necessary bone, and it results in a lot of issues. And finally, on the far, my left, on your right, you see Richard Lee Norris. Richard Lee Norris was shot in the face with a shotgun at the age of 19. This is Richard Lee Norris after 18 reconstructive surgeries to try and restore function to his face. Now, what's really common across all of these patients? They're all very different, children, adults, youth. What's really common is that they're all missing a large quantity of bone. We really need bone to treat these patients. Let's investigate one of these cases more closely. Richard Lee Norris. Here's Richard Lee Norris at 19. I think this is the night of his senior prom in high school. No one really knows what happened. Some people think it's a suicide attempt. Some people think he was shot in the face as a prank by mistake or a hunting accident. But basically, shot in the face, rushed to the emergency room. 3 years and 18 surgeries later, this is what he looked like. So we can see that he's missing an enormous amount of bone. I mean, from his eyes down and above his eyebrows, it's completely obliterated. He has no bone structure left, and the MRI scan literally shows a flat face. He cannot speak, he cannot taste, he cannot smell, he cannot hear, he cannot see, and his breathing is controlled by a tube that comes out of his neck down below. This is Richard Lee Norris 2 days after the world's most successful full face transplant procedure performed by Dr. Eduardo Rodriguez at the University of Maryland. This is Richard Lee Norris 116 days after surgery, and this is Richard Lee Norris today. Wow. This is Nobel Prize worthy work. This is unbelievable result of what came out. I mean, as you see, the final picture is 15 years later than the original picture in the bow tie, and I mean, this is what he would look like if he aged naturally. The surgeon was promoted after this, but he did very well. But the point is that, as you can see, you can imagine how much bone, the face and the underlying bone structure was taken from a boy that died in a car accident, actually. Richard Lee Norris got really lucky. He found a donor who matched him perfectly with size, shape, amount of bone structure. The other patients that you saw on the slide before, and most patients aren't this lucky. Bone is this incredibly dynamic tissue. Dynamic means that people don't know is that bone is really like your hair and your nails. Bone is constantly regrowing and reforming. There are cells called osteoclasts, which eat away at your bone, and there are cells called osteoblasts, which regrow the bone. Bone is surrounded on the outside by this white layer called cortical or compact bone. This is what you see when you think of bones, think of the white layer. And the inside is what's called trabecular, or spongy bone. This is a sponge, and it contains the bone marrow and the blood vessels necessary for the nutrients. So currently, what doctors do when they need bone is they do what's called a bone graft. A bone graft is literally taking bone from somewhere where it is and bringing it to somewhere where you need it. The Department of Defense estimates that there are 2 million of these bone grafts done every single year, and they fall under the umbrella terms of autologous, which means that they come from your own body. Let's say someone needs bone in their skull, they bring it from their leg or from their rib cage. And allograft. Allograft means that it comes from a member of the same species, so another human body or a cadaver, and brought into a living human who needs it. These face enormous complications. The complication list starts with a rejection. The body simply will not accept it, just like it will not accept any random donated tissue. There's size limitations. You can only take so big a piece from yourself or from someone else. The piece doesn't fit the gap that it needs to fit. This piece brings diseases with it from the donor, and so on. So what our lab has basically said is that there must be a better way. Our solution as a laboratory is to develop a scaffold, kind of this concrete piece of material, that takes the shape of the gap in bone that we need, And it's biocompatible, which means the body does not reject it, and it's biodegradable, which means that it breaks down inside the body. So our goal is for this to guide the body in growing its own bone. Really, if someone needs bone and they're able to grow their own, this is really the ideal, because then the body cannot reject it and it will fill the space perfectly for what's inside of it. This is called tissue regeneration. Tissue regeneration is the science of growing any kind of body tissue in the lab. This ranges from growing skin cells to there's a laboratory in Chicago that just grew a full functioning kidney to be used for transplants. Tissue regeneration is made up of three major components. One, you need a scaffold, something that will hold the necessary components to take the shape of the thing you are growing. Two, you need cells. And three, you need growth factors. We'll talk about all these things. Only together can these three things kind of make a successful and healthy tissue. Now, you've all heard of stem cells. Stem cells are kind of the wave of the future in medicine. This is, stem cells could potentially be responsible for numerous cures of all sorts of ailments within the next 10 to 100 years. Stem cells come from both human embryos, they come from fetuses, which are kind of a more controversial area of medicine, and they come from adults, which are us. You all have stem cells in your fat, in your hair, in your nail beds, etc. Stem cells exhibit this quality that's called multipotency. Multipotency means the ability to become any kind of tissue in the body with the necessary pushing. Stem cells start off as blank. They just float around in your body, and they haven't taken on any characteristics yet. So we can urge them in ways to become certain types of tissues. We will use BMMSCs, bone marrow-derived mesenchymal stem cells, and HUVEC, human umbilical vein endothelial cells. You don't have to remember this, just bone marrow cells come from your bone marrow, and human umbilical cord cells come from your umbilical cord. The growth factor that we want to look at is bone morphogenetic protein 2, which I will call BMP2 from going forward. BMP2 is literally a small protein that when it sees a cell, it makes the cell become bone. And it pushes the cell to become bone. So this is how we take stem cells and we combine them with this growth factor, and together we're going to grow healthy bone. That's the ideal, at least. Now, bone morphogenetic protein 2 is actually already approved by the Food and Drug Administration of America for use in surgery of the spine. Sometimes people require a surgery called spinal fusion, where they need pieces of their skull to kind of fuse together for treatment. Now, what surgeons do is they take a lot of this BMP2 and they kind of squirt it into the back. Random doses, there's no real calculation for it. They sew up the back and they let the person go on their way. The idea is that it grows bone, but the problem is that this faces also enormous complications in that we see seroma formation. Seroma is kind of pockets of fluid that really are pretty harmless but can lead to more complications, especially extreme pain. And the main complication is called heterotopic ossification. This is bone growth that happens outside of the normal skeleton. It's kind of hard to see here, but this is an x-ray of a 45-year-old man who had BMP2 used in a hip surgery. And all of this kind of like cloudy white stuff, this is bone that's growing out of his hip. You can imagine that that's not so pleasant or healthy. So what we see is that a high dosage of BMP really like overwhelms the body and does really bad things to it. It's a very strong protein, and the body kind of freaks out when it gets too much of it and grows way too much bone. So what we see is that we really need a necessity of a controlled dose. We can't do too low a dose because too low a dose of a protein won't affect the body and we'll just ignore it. So our lab thinks the best thing to do is to administer a very small amount of BMP2 but over a very long period of time, because then the body will keep reacting slowly and grow healthy, good bone without these complications. So this is our kind of like major question, is can we avoid the side effects that we saw by releasing the BMP2 in a slow and careful manner as not to overwhelm the body? Because really this is very dangerous. So let's just pause for a moment and look back. We saw a problem in plastic surgery where we need bone for people's faces and their skulls. Our lab doesn't like the current standard of care, which is bone graft. So what we decided to do is we decided to design a system which we grow our own bone. So the system involves one, a scaffold, which we'll get to, two, stem cells, which I showed you, and three, bone morphogenetic protein 2. But the problem is that the BMP2 is too strong. So really the core of our research comes down to this idea of administering the protein in a slow and careful way. Our lab has developed these things called microspheres. Microspheres are literally tiny balls of plastic. And what we do with these balls of plastic is we fill them with the protein and the growth factor, with BMP2. And the plastic is called polylactic co-glycolic acid. It's a biodegradable polymer that breaks down slowly in the body. So as these spheres break down, the insides come out very slowly. And therefore, we can let the body get a low controlled dose of the protein over a long period of time. These are what these spheres look like. They come in all different shapes and sizes, as you can see. We can customize them any way we want. But if you just look at the big ones, you kind of see these little droplets in here. This is protein that's suspended inside the sphere. This is what we call a release kinetics curve. Basically, we inject these into kind of a cell body, and we want to see how they react. So our hypothesis was supported that really we see that about 50% of the protein is released after 5 days, and the rest is released over the next 35 days. So what we see is that the protein is coming out almost over a month, which is exactly what we want. It's a controlled, careful release of the protein. I want to pause again, because I really want you guys to understand this. This is a beautiful concept. We saw a problem that exists in the operating room with people, just like us, younger than us, older than us, our age. And we broke this down over the course of 1 year to the point that the solution to this may lie in a microscopic piece of plastic. And this really, I think, expresses the joining of basic science research in a laboratory and the world that we live in. So a lot of people think that this kind of mindless labor that you do at the lab bench with test tubes and pipettes is just useless. It's not. This is what this is. These microspheres are developed over many, many, many hours of sitting under a hood very late into the night. We spent 1 year just developing these microspheres. And this could be the key to a major issue in facial plastics. So we're ready to kind of use this in an animal model. Our first animal model is called a nude mouse model. And what we do is we call this a proof of concept model. The reason we call it proof of concept is because mice are obviously not applicable to humans. If something happens in a mouse, we cannot say for sure it's going to happen in a person. But mice are the kind of the lowest animal form in research. And so what we're going to do is we're going to inject our experimental stuff into the mouse. And if it works in the mouse, then we can say with some degree of certainty that we should continue our project. If the mouse dies right away, then obviously we have to go back to the drawing board. Nude mice are special mice that have their immune system removed so that they cannot react to whatever we're putting inside them so that they don't have an infection. They're called nude because the lack of an immune system doesn't allow them to grow hair, actually. So the scalpel we'll use is called Matrigel. Matrigel is kind of a pink toothpaste-esque material that when you inject it into the body at body temperature, it hardens. So we can fill a void with it and it will take the shape of whatever we want it to take. The cells we'll use, as I mentioned before, are BMMSCs, the stem cells derived from your bone marrow. These are actually derived from rabbit bone marrow because that is the lowest form that we were able to isolate the cells from. And the growth factor is, again, BMP2. I don't want to get into the nitty-gritty of the procedure, but basically we took 8 mice and we put the mice under anesthesia. And in a sterile facility, we injected each of the mice with 4 implants. You can see down here there's 1, 2, 3, 4 implants. Kind of look like little tumors, little balls that are right underneath the surface of the mouse. These are injected literally right underneath the skin so that there's an infinite blood supply because the skin has a lot of blood vessels. It's very important to understand the groups that we injected. The first injection that we did, which is right here, we did with only the scaffold. There was nothing else there. This is called a control group. We do not expect any bone to grow here. We just want to show for sure that the scaffold is not responsible for any bone growth on its own. The second group is our experimental group. This is the Matrigel with the cells and our microspheres, the balls that contain the growth factor. And our last 2 groups are really important because they're high free dose and low free dose. These doses of BMP are not, they're not injected into microspheres, they're literally just squirted into the mouse's body. And this is kind of what they do in the operating room. So we want to show that our technique is better than what they do in the operating room. What this is called histology. Histology is the analysis of tissue, and what we do is we take very thin slices. I apologize for this white line. We take very thin slices of the 4 implants and we stain them with special chemicals. And the chemicals tell us what's going on. Basically what you have to know is that light pink means nothing happened, and dark pink and purple means that bone was formed. So in our control group, where we just injected the scaffold, obviously nothing happened. It's just pink, there's no bone, which is exactly what we expected. The second group, which is just a low dose of the protein just freely poured into the body, again, nothing happened, which is why I said earlier that just a low dose, the body won't react to it. Here we see our high dose. This is what the surgeons do currently in the operating room. They just kind of overwhelm the body with the amount of protein to grow bone. We do see some bone formation here, but that's expected also. The important group is right here. As you can see, our microsphere group, on the same scale as these pictures, created almost an entirely bony structure in this sphere. This is really a remarkable result, that the purple and the white is pure bone that was formed, calcified bone. After only 4 weeks, we were able to grow a ball of bone in the mouse. Just for you guys to understand, the total dose of protein in all of these microspheres is less than the dose that was just poured into the body right here in the free dosage. So really our model does work. We've proved our concept and are ready to move on to our bigger animal model, which is a rabbit. Why do we use rabbits? Rabbits are the lowest species that are accepted in evolution, for which if something happens in their skull or their face, we have a high degree of certainty that it will also happen in the skull or face of a human. I know it doesn't look like it, but rabbits actually have the same face anatomy as humans. So we use New Zealand white rabbits. They're your average white fluffy rabbit. We again use BMMSCs and our bone morphogenetic protein 2, or BMP2. And the scaffold we use is Duragen. Duragen is just a white sponge that's sterile that can be cut in any shape that you want, so we can put it in the body. One more time, we won't focus too much on the procedure, but basically we take the mouse. And this, the rabbits now, because they're a big animal, we have to use a class 5 system. Class 5 means that rabbits are treated like humans are in the operating room. So we use a full-size operating room, just the same kind where humans are operated on. We use anesthesiologists, and there are 2 surgeons, myself and one other surgeon. And on a sterile operating room, we cut open the top of the rabbit's head, and we drill 2 holes in the back of the rabbit's skull, all the way down to the bone, to the brain, sorry. And then what we did is we took discs of this kind of Duragen. This is what it looks like without anything in it. And the pink is what it looks like when we inject our microspheres and our cells inside of it. And we put these into the rabbit and we sewed it up. And then we let the rabbit live for 8 weeks, and then we sacrifice the rabbits and we take out their skulls to analyze for bone growth. This is a quick picture just to show our operating room setup. This is what it looks like. Apologize, that is gruesome. I'll switch it quickly. But basically, you see the 2 holes that are formed here, and then you see the implants that are put in here. So the groups that were used in the surgery were the same as the groups that we used in the mice. So what we want to see here is that this is called a CT image. It's microcomputer tomography. What it does is it takes very thin slices of the bone over many hours, and it eventually gives you a fully constructed view of the bone in very high definition. What you need to know is that green is bone and blue is nothing. So here are a lot of our control groups. This is just an empty hole. We just drilled a hole, and as you can imagine, nothing grew. That makes sense. The second one, we just put in a piece of our scaffold, our Duragen. Again, nothing grew. Makes sense. The third group, we just put in a bunch of stem cells. Nothing grew because there was nothing in there to tell those stem cells what to become. We didn't have our protein there to push our stem cells to become bone. And finally, our last group was similar to that low dose of free protein that we did in the mice. This was the scaffold and the stem cells and some of the protein, but the protein was just squirted in there like they do in the operating room without any microspheres. Now this is pretty cool. This is our experimental group. Here we have a scaffold again. This is just a control group with nothing in it but the scaffold. Obviously nothing formed. Here, however, we see the same size hole as here with our scaffold, our stem cells, and our microspheres. And as you can see, almost the entire hole is closed with full thickness bone. The bone is the same thickness as this down here. That was analyzed through a different technique, but really this is amazing. I mean, this has proven the fact that we can take a very low dose over a long period of time and produce a result that is far better than what's seen of a similar dose just squared. This dose in the fully closed hole is the same dose as you see here in this control group, but instead it's released over a long period of time, very carefully and very slowly, using those microspheres that we developed. This is really, I want to stress how remarkable of a result that this is. This eliminates a lot of the issues that have been seen thus far in the operating room with these types of surgeries. Here's a zoomed out view of all 4 of the holes. Again, all of our control groups and our experimental group right here. Obviously, 100% better than any of the other groups. Now, we have to look back at our original question. Our question stated that not only do we want to see if we can grow bone with a controlled dose, we want to see if we can avoid both of those complications. The complications I mentioned were seroma, that fluid forming, but especially the bone that grows outside of the body, the extra bone. To test this, we gave one of the rabbits an extremely high dosage of BMP2. We gave it a dosage that's 300 times higher than what we gave to our microsphere groups. And this most closely mimics what they do in the operating room. They soak a sponge in a lot of this. It's called a supraphysiological dose. It's a dose that goes beyond the capabilities of the human body and overwhelm the body with this protein. So at first glance, you think, this is amazing. I mean, both holes are fully closed. It's better than the experimental group. But the important thing to note here is that if you look back at these groups, along with these groups, if you look carefully, you can see these zigzaggy lines here, all the way down, all the way down. These are what we call sutures in the skull. Sutures are where your skull forms as a baby, where the plates join. They form in these kind of interlocked structures that are called sutures. Now, while they look just like lines, they're essential to the anatomy and the function of your face and of your skull. Without them, a lot of the blood supply to your skull and to your brain is obliterated. A lot of other issues arise with surgery and so on. And as you can see here, there is no line like this going down. There's no zigzaggy line. This is the perfect and first time in the laboratory that we've recorded proof of heterotopic ossification forming in the skull like this. This is even more unbelievable that we have shown that our bone, well, yeah, it doesn't form perfectly the whole hole, but this is only after 8 weeks. It forms almost the whole hole and keeps the line that's running down the center of the bone. This is truly, truly amazing. As you can see here, it's kind of hard to interpret this image, but the white here is the bone that's surrounding a cell. This white should also have ridges in it on a cellular, molecular basis, and it doesn't, which is another perfect example of heterotopic ossification. This is extremely, extremely important because we have truly proved our hypothesis, and this is the conclusion of our experiment. It's really not over. Research is never over. We have a lot more to do. We published a paper on this result. This talk was given at a symposium a few months ago. But now we want to kind of standardize the formation of microspheres. We want to make microspheres that are the same size every single time so we can give them to surgeons in the operating room and tell them, you guys are for sure using microspheres that are exactly 1/10 of a millimeter wide every single time. We actually just did this. Last week we completed a protocol which successfully created the same exact microsphere 100 million times. We want to do new rounds of surgery with more rabbits, but fewer experimental groups. We just want to prove continuously that our model works every single time. I'm being charged recently, my recent project in the laboratory for the last half a year is engineering periosteum. I won't go into the details of this, but periosteum is this fibrous layer. It looks kind of like an Under Armour shirt that's white, that's stretched over all the bone in your body. And it basically supplies the bone and the bone marrow and other structures inside the bone with a blood vessel supply and nutrients. Very important. And our model doesn't account for it right now, so I'm using a technique called electrospinning to try and create artificial periosteum in the laboratory. Most importantly, I want you to see the main message here. We saw a problem that arises in the operating room in the clinic. My primary investigator in the laboratory is a plastic surgeon. He treats these patients every single day, and I go with him to the hospital to see these patients every single day. These patients are real live people. And one day, 5 years ago or 4 years ago, Dr. Taylor, who's the plastic surgeon, came into my lab and said, we have to fix this. We have to address this issue, and we're going to do this. So in the course of 3 years, we broke down this concept from a human thing all the way down to a microscopic level, to a level of a microsphere on a cellular basis. And then we brought it very carefully all the way up to the evolutionary ladder of different animals up to a human again. We have not yet tested this on humans. This will happen within the next 5 years. And this is really a perfect example of how research is not some boring topic that you kind of sit and do at a lab, but this is real life application of something. And I really want that, that's kind of the main message here. If you didn't understand the project, that's okay. Just see that we kind of took a problem, had a concept, proved the concept, and we're very close to bringing this to the operating room for real people, people that could be related to you, people that could be you. And I really think that that's the most remarkable thing. Just real quick, I want to thank, I'm not going to read the full slide, but these are all the lab members and all those organizations that support us. So yeah, thank you.
Unfortunately, we don't have time for questions right now, but Rami, you'll be in classes later today, so you will have a chance to talk to Rami if you would like to.